Hello everyone, welcome to the first session of particle physics. I'm very glad to make this playlist, and I'm trying to approach particle physics from experimental, phenomenological and theoretical point of view. Like the term medical science, imagine it's a very broad term. It can refer to any part of medical science. You have experts in eyes, expert in cardiology and any other branches of medical science. So particle physics is like, it's a similar term. So you can have cosmic rays, you have the physics of LHC, heavy ion collision, and you have so many eras in particle physics. Dark matter detection, neutrino physics, and they're all kind of different. So people spend their life trying to be expert in any of these fields and try to navigate through one of these measurements. Usually, the gap between theoretical knowledge, theoretical models to the experimental observables is very complicated because you have a lot of complexity, and usually this complexity is studied through these phenomenological models. So to connect experiment to theory, we have to be careful that there are a very high level of complexity, and probably we need to understand particle physics from all of these 3 points of view. And of course, if you are an expert, if you are working on theoretical calculation, it's a very different kind of practice. And if you're experimental physicist, it's a very different practice. And if you're doing simulations, it's a kind of different all kinds of activities. But at the end, the whole integrated knowledge about a standard model and how quarks and leptons and the force carriers interact is the subject of particle physics. And we're trying to understand why we have this standard model and how did we get this picture and what led into the current picture of the universe that we have. So I chose this image from a cloud chamber. If you go to many institutions, they have this image of kind of cloud chambers that have the traces of the charged particle, that they have this spiral pattern. And this spiral pattern is because they're moving in a magnetic field. And in the early days, people were manually measuring the radius of these spiral patterns to do actual measurement, to measure momentum of these particles, to measure the mass or charge of these particles indirectly. And it's kind of this is the essence of particle physics, that if you have a trace of this particle, then you can calculate their properties, and you can have some indirect measurement on those particles. There are basically two devices that were so essential in the 20th century about the advancement in particle physics. One is the cloud chamber, and the other one is the bubble chamber. Cloud chamber was invented by Charles Thomson Wilson, or Wilson cloud chamber. It's famous for that, and he got a Nobel Prize for that in 1911. He invented the device, and the primary function of that device was to detect cosmic rays. And the chamber is kind of filled with a gas. The gas is usually non-reactive, and it can be ionized or polarized, mostly based on ionization. So when a charged particle, something like a cosmic ray, is coming into the chamber, it hits some of these atoms. For example, it can be a CO2, it can be argon gas, and then it ejects an electron outside, and this electron have a trace. And the trace of it is something that you can see because of the concentration of the atoms in the chamber. And on the left-hand side, you can see the bubble chamber invented by Donald Glaser. And this is the very important invention because the bubble chamber was the most sophisticated form of cloud chamber. Similar functionality, but instead of a gas, it was using a superheated fluid. And the superheated fluid is special because any part of the superheated fluid which is triggered by a charged particle, such as the electron, even low energy. So the whole point is that this superheated fluid is more sensitive to low energy particles. So it could create these bubbles, and these bubbles were that kind of trace that the charged particle will have, where charged particles have on the indirect interaction with the atoms. So this bubble chamber, for example, used to detect neutrinos. Neutrinos are not even charged particles, but when a neutrino is absorbed by some atom, then it can release an electron. So this electron is a kind of secondary sign of the neutrino interaction. So therefore, the neutrino detection in the Gargamel experiment in CERN was done through a bubble chamber. And these two devices, they were able to really advance the field of particle physics by creating a framework of how to make the trajectory of the charged particle. So if you have a charged particle, or sometimes even uncharged particle, if you have a medium that how that charged particle interact with the medium, then the problem is always about how to make a good device that it is really calibrated and basically something that you really well know how do they interact with the charged particles, and then you basically have the trajectories of charged particle, and then from the quantities of those trajectories and from their quality, you can assess some physics data. So these two devices were so essential in the 20th century to advance this field and make us, make us be able to do more accurate scattering experiments. How do we have such accurate measurements in particle physics? It's a very kind of, I tried to make some questions that I had when I was younger, and I was always like, how do we have such accurate measurements? Sometimes you hear that the physicists were saying that we measured something up to 8 digits, and you're surprised how accurate they can be, because sometimes if you try to do some measurement by yourself, even simple one, measurements in general are hard. But especially when you look at the mass of this particle, the mass of this particle are extremely smaller than the mass of our macroscopic world, or compared to one human. Imagine a human is in the order of magnitude of 1 kilogram, 10 kilogram, 100 kilogram. I mean, this is the macroscopic object around us, but the mass of the electron is 10 to the power of minus 31 kilogram. And if you want to think about order of magnitude, you probably hear about kilobyte, megabyte, gigabyte, and terabyte. And now if you follow that logic, you notice that the mass of the electron is so much smaller than the mass of our macroscopic world. So you cannot really manipulate these objects easily in a high energy experiment. For example, Robert Millikan manipulated the oil drops to measure the charge of the electron, but in high energy physics, most of these particles are moving with a very, very high speed. So, and they have a very small mass. So you should not really disturb them to measure them. That's a very important principle. So, you cannot manipulate this particle. You cannot tie them to some point using strings, using, suspension of those particles. This is not the subject of the high energy experiment. Usually you have to deal with very, very energetic particles, and the whole way, probably the most of the way that you understand how the energetic particle have some characteristic is how does it interact with the medium. So if you have a medium, and if you know that medium very well, like cloud chamber, bubble chamber, you can basically calculate how much ionization you observe if one electron with that mass or one proton with that mass is crossing by that medium. So that's very important, that these measurements are all indirect, and you're measuring a lot of samples. And when you measure a lot of samples, that would reduce your error bars. So you have huge error bars in these experiments. So, you cannot just measure 1, 2, 3 times. You have to measure it, for example, 1 million times, 1 million sample, 1 billion sample. It depends on what you're measuring. But, the whole point is that if you have very, very small masses and you have very, very high energy particles, there are two keys that make these measurements very accurate. And that is indirect measurements, models, and also having huge amount of samples that will help you to reduce this statistical fluctuation, because you have to deal with a lot of fluctuation. And the nature of this research was always evolutionary. So we have these detectors right now, very advanced detectors, and you might ask, how they're so advanced? And this is not like a one-night job. It was a constant evolution of devices. So each part of the device was used in the next generation. Sometimes new whole layers of detectors were designed. But we need to understand that we are making detectors for 50, 60, 70 years, and humans and engineers and physicists in different experiments, they became very good at making detectors and calibrating them and knowing how do they interact. So we were able to go into the physics data. So if your detector is bad, if your detector is inaccurate, then all you get is a bunch of noise. All you get is a bunch of charged particle. There is no meaning into that. But we're following a trend of doing particle physics for a long time and extracting physics data from very, very accurate detectors. And people are working in this detector, like in CERN, for more than 50, 60 years. So several generations of engineers and physicists and data scientists were working on to make this current framework. So everything we use today has root in a huge, complicated evolution and the contribution of so many people. At the early days, everything was analog and there was no digitalization. Everything was, recorded in papers, tables, and the data was not digitalized. And sometimes even people have to use rulers and manual devices to measure curvatures, distances, and this kind of measurements. So everything was analog at the beginning, and nowadays everything is basically digitalized. So the current LHC, for example, experiment, there are 4 experiments in LHC, but 3 of them are like these large detectors, and ALICE, Atlas, and CMS. Also, there is also LHCb, which has a different nature, but these 3, they are heavy ion detectors, but they're designed for special tasks that they were designed for. ALICE is primarily designed to investigate quark, gluon plasma, or thermal properties of heavy ion collision, and CMS and Atlas were mostly designed to study jets, high energy particles, massive particles, Higgs detection, supersymmetry detections, and so on. And they have a different purpose, but the whole point is that you can see these trajectories are right now digitalized. And now since they're digitalized and they are stored in the digital format, huge data manipulation can be done through them. And for example, you can get rid of noises, fluctuations, and probably the most important problem that you have to deal when you are doing this kind of experiment is to how to get rid of noise, how to get rid of background, how to calibrate the detector. And because of these digital tools right now, the task is so much better right now. And with the tools, new tools like machine learning, this is just becoming even more and more better, because now you don't have the bias, because bias is a very important part of experimental physics. You always have to be careful that you shouldn't have bias towards something. It means that you have a parameter that you're not aware that it has a huge impact on your final outcome, and then you try to interpret the final outcome as physics. So bias is always important, and with this digitalization and new statistical methods, one can argue that how can we get rid of this bias. Now another question: what do we mean by standard model? Standard model, you probably hear the term standard model of particle. There's also standard model of cosmology. I'm starting from a standard model of cosmology. Actually, that doesn't mean the standard model of cosmology. But this is the standard picture that we recently got from the whole structure of the universe. Before this century, 20th century, we didn't have the tools to study galaxies, so we really didn't know about larger structures, and this was only available to us now. And the image of the universe is more evolved in this way, that there was a current state of the universe which is cold and very large, and there are evidences like cosmic radiation background that the universe at some point was very dense and very hot in terms of temperature, and it was so much hotter than the current state of the universe. So therefore, the ordinary matter that we see today was not available at that time. So the early universe, might have been like a soup, and everything was, in a very hot, dense environment going around, and really didn't make any stable structure. And as the universe kind of started to cool off, the structures started to emerge out, such as the hydrogen atoms were formed. But before that, we have these quarks, and quarks were going around freely, and then they have to hadronize. So they make these hadrons, and then hadrons made proton, neutrons, and then proton and neutron came together to make nuclei, and then nuclei and the electrons made atoms, mostly hydrogen at the beginning, helium, lithium, and then first generation of stars were formed, and then first generation of galaxies, and then galaxies created more stars. So the third generation of stars is our sun, and solar system is like a product of this whole universe evolution. So this is like the model standard picture that we have in cosmology. We really didn't have the tool in the last century, until the last century, to get to this image. Other than that, we had some guess. Cosmology was mostly in the territory of philosophy, because people didn't have good telescope to go more than that and to really distinguish galaxy until the beginning of the 20th century. The telescopes were good enough to notice that the galaxies were not stars, but basically like islands of stars very, very far away. But I'm not a cosmologist, and so I go to a standard model of particles, a standard model of elementary particles. And a standard model of elementary particle is an image that we eventually accumulated in the last 50 years. And it wasn't just sudden that we have this image. And this is like a periodic table of the current state of the universe. At 100 years ago, again, people were thinking elements were, gold, aluminum, oxygen. They could not explain what is really the reason that these elements are different. And then they found out that the number of the electrons and protons are different. And then they eventually realized that proton and neutron themselves can be decomposed into the quarks. And this is probably the biggest advancement of the 20th century, that in the 50s and 60s, we were able to see the protons and neutrons were made out of quarks. And we eventually realized there are 6 generations of quarks, 6 generations of leptons, and there are basically 3 forces that they could all be explained by an underlying principle known as gauge invariance, and then the Higgs boson, which is responsible to give mass to all of these particles. Higgs boson were discovered later in the 2010, and compared to these, it comes later. But in general, this is a standard model, and then I'm going to explain more about the standard model. But this is the particles that right now we don't know if they have more particles inside of them. So, the other branches of physics, such as string theory and other theories, alternative theories, who are trying to explain, for example, gravity, also in this context, they try to explain why do we have different types of particles, and why do they have different masses, or they have different charges. And, at this point, we can always wonder, why do they have certain masses or certain charges? But I think this can be also studied within the physics, but you need the physics of higher energy, and that higher energy is something that it is so much higher than the current accessible energy for us right now. So that is in the territory of Planck mass, Planck energy, and very, very high energy. you probably hear this phrase that most of the atom is empty space, and the analogy they use is this soccer stadium, and probably the nucleus is in the center like a soccer ball. So I know the size of the soccer ball here is exaggerated, it's so large, but it looks like that the majority of the mass is concentrated into the soccer ball. Because I have a problem with this analogy that the atom is empty, because electrons are considered to be individual little particles that they don't have any mass and they are just around. So the majority of the space is empty. So first, the first thing that you probably have to encounter is that even in the Schrödinger picture, or quantum mechanical version of the hydrogen atom, the electron is not a particle. It can have a wave function, and the wave function extends into all points of space. So therefore, all the space is not basically empty. It has content. It has electron content. But even if you think that the electrons are basically particle, which is more compatible with the Bohr's image, again, the empty space in between is filled with the electromagnetic radiation. So it's not really empty. Empty means like there is no energy content. Empty doesn't essentially means that there is matter inside. You can have radiation. You can even have quantum fluctuation. So you don't really have really empty space. You always have some content into that. So the point of saying that the whole atom is empty is mostly mean that the majority of the mass is concentrated in the center. And, the whole space doesn't have that much mass, but it does have content. So this is a standard model. For example, we can divide these particles into two groups, fermions and bosons. And fermions are matter. So fermions are matter. So matter is, it's kind of, need some advanced mathematics to see what's matter. Matter is something that can be explained by, for example, in the case of fermions, there are Grassmann numbers to kind of represent them, and then ordinary number for the gauge fields. But it doesn't matter. Let's say matter is something distinguished from radiation. So radiation is like more free. Radiation is the way that the matter communicates. So two matter particles, they cannot talk to each other without radiation. So radiation is that channel to link two particles to interact with each other. So in general, you say there is two groups, fermions and bosons. Fermions are matter, bosons are radiation or force carrier, or channels to speak for the fermions to each other. And fermions, they have the spin, half integer spin, and if they have half integer spin, their nature is somehow different from the nature of the boson. Then they can basically occupy the energy state only one fermion at the same time. So not any two fermion cannot be in the same quantum state, and therefore the matter in the universe is kind of stabilized. Atoms are stabilized because at some point people were asking the question that why does the electron is not directly going to the center of the atom and be destroyed. It was this kind of puzzle, because based on electromagnetism, they should radiate their energy and then go to the center. And somehow quantum mechanical description later kind of gave us this image that fermions, they cannot all go into the same energy state. So each of them feels one energy state, so they are like a ladder on top of each other. And therefore it creates something that we call it Fermi energy. And this Fermi energy is something that is based on the height of how much electron you have to fill this energy gap. And you have these force carriers. Force carriers are three. So we say we don't have gravity here. And the reason, again, we don't have gravity is that these particles are really, really small, so they don't have that much mass. So in the context of gravity, they don't do anything. They don't bend the space-time that much. So the standard model that we talk about doesn't incorporate gravity. It doesn't mean that you should really, at some point, gravity also should be unified with other forces. But, it's happening in a very, very high energy, not at the scale of LHC. In the scale of LHC, the space-time is flat. The masses are negligible, therefore you don't really have to be worried about the mass of the elementary particle really changing space-time that much. But there are three interactions that they can be unified into a framework. By unification, it means that you can explain at high energy, they are not distinguishable really from each other. Right now they are distinguishable because they are responsible for different processes. Photon is responsible for carrying the electromagnetic radiation, or basically energy momentum by the mean of electric charge between the two fermions. Gluon is responsible to carry the strong force, responsible for binding quarks together to form protons. So gluons and photons are so essential for our life. Because we have gluons, we have protons, we have neutrons. Because we have photons, we have atoms, because the proton and neutron should be connected to the electrons. And therefore, most of the life is explained through gluons and photons. The weak interaction is a little bit different. It's because their force carrier is massive. And therefore, because they're massive, they basically tends to mostly explain decay processes, rather than constant two-sided interactions. So the decay processes and weak interactions are mostly asymmetrical interactions, and maybe they're responsible for certain symmetry breaking. I could explain the abundance of matter in the universe. It's called CP violation, maybe. So the CP violation and baryogenesis are the context to explain why do we have a matter-dominated universe. So there is asymmetry in the weak interaction, and weak interaction is different. And again, it's because it has mass. The weak interaction is very short range. They don't have mass, so gluon and photon don't have mass. In particle physics, when a particle doesn't have mass, classical physics cannot explain that. So in classical physics, you always have to have mass. But in electrodynamic, you can see that the electromagnetic field can propagate with the speed of light. That's the equivalent of having a particle that is massless. And in the quantum field theory, you can basically construct this argument that there are particles that are kind of massless. So therefore, they move with the speed of light. And photon and gluon, they move with the speed of light. And these are the components of the universe that are fast in the context of, carrying the force in a short amount of time. What is the net distribution of matter? It depends. If you're asking about Earth, you have oxygen, silicon, and then aluminum, and the other elements. So it's because Earth is mostly a rocky planet. But if you look at the universe, atoms in the universe, 74% is hydrogen, 24% helium, and then the rest. So in the universe, most of the universe is hydrogen. It makes sense because hydrogen is the simplest atom. It's one proton, one electron. And if you think about the other atoms, they're more complicated. You need more kind of extreme condition to make them. But even if you look at the whole energy content of the universe, that's interesting because you see, maybe I should change my image here so you can see that only this whole hydrogen and helium, they integrate all to 4% of the energy content of the universe, or so what we called it a baryonic matter. A baryonic matter is the ordinary, basically, atoms that they have baryons inside of the nuclei. But you have 22% of something that you call it dark matter, and 74% that you call it dark energy. And for dark matter, you don't have a standard model description. You don't know what particle they are. That they have a huge gravity, but they don't have any kind of electromagnetic interaction. So, some theories like supersymmetry, they try to explain how can we have candidates for dark matter. But this is something that is ongoing. We don't know, and it's one of the probably exciting points of physics at this point because we don't know what it is, dark matter. We know that it's there because of the gravity, and if you look at the motion of the galaxies, the evolution of the galaxies, and the behavior of the stars in the galaxy, the speed of the rotation, you notice that it can be explained if you have a halo of dark matter around. So usually, if you look at the galaxy, the disk of the galaxy or the baryonic disk is like a kind of flat disk, and then there is a spherical halo of dark matter around it. So, and we don't know what it is. So, just want to say that. Then the question is like, what is matter? Because in that context, what we call it a matter is only 4% of the content of the world, and the majority of them we don't know what it is. And it's interesting because people are saying physics is a science of people are saying that physics is a science of matter and radiation. Well, the matter and radiation that we know is not really huge amount of the constituent of the universe. We know the majority of them, we don't know what it is, and it's dark matter, dark energy. So, the majority of the quarks, for example, are up and down in the universe. In a normal condition, you cannot really make higher state quarks. So proton and neutron, they only have up and down quark. But for example, in the core of the neutron star, because the pressure and the gravity is a lot, pressure and temperature are high, you might have quark-gluon plasma, maybe in the solid form, inside of the core of the neutron star. So you might even have a strange quark. And again, if you compare the mass of the strange quark to mass of the up and down quark, it's 2 orders of magnitude larger. So in particle physics, we express all the masses based on the unit of MeV or electron volts, EV electron volts. So it can be MeV, GeV. That's the unit that we use. It's kind of nonsense to use units such as kilogram because, you don't want to deal with very, very small numbers. So you always have the freedom to change the unit to something that is like number of 1, 2, 3, 10. It has a meaning for you. So the mass of the up and down quark are 2 MeV, 4 MeV, and then you have this strange quark with a mass of almost 100 MeV, and then that's interesting because it's kind of heavy compared to these two. But you can have even a strange quark inside of the neutron stars, and there are even interesting argument about a strange matter that is really science fictional but very cool. But the rest of the standard model is not something that you find in the natural world and in the current energy of the world, because you don't have energy to make charm, bottom quark, or eventually tau muon. So these are extremely kind of heavy. You have to make them in the lab. So in the high energy experiment, when you collide proton with a very, very high energy, then you have enough energy to create these particles. And you also have all these types of neutrinos, because neutrinos kind of oscillate. So there is a huge amount of also neutrinos in the world, and neutrinos are similar to ghost particles. They are not electrically charged, so they only interact through weak interaction. Therefore, you really need a very, very different approach to detect them compared to heavy ion collision. So neutrinos are, everywhere, and they are produced in a huge amount in the stars and everywhere, and they're going through, and the detections of them is a very different story. Are two electrons identical? Imagine that you have two same car that they are all produced in the same factory and the same assembly line, and but they have a different plate. So I mean, they are different cars. I mean, even though they are completely identical. So it has a meaning for us, for example, to think that macroscopic objects are not identical because they're different. And a very interesting example of it is in this twin brothers and twin sisters. When you have the identical twins, they have the same DNA sequencing. So that doesn't mean that they have the same DNA, and that's the whole point of it. You have the same sequencing, so the DNA is basically duplicate, but as it starts to evolve, it has a completely distinguishable nature. So the two DNAs start to evolve differently, so therefore their configuration is always different. So therefore, again, they are a macroscopic object. So in the macroscopic world, things are not identical. And if you're familiar with the story of Tintin, there are two detective brothers, and these two brothers are identical twin, but if you look at the shape of their mustache, it's different. So even they have the same DNA, but it shows that they have two different characters. One of them likes to make their mustache different from the other one, so they are not identical. But the first time Americans, sorry, I have to move my video here, but I want to show you this formula that an American physicist, Willard Gibbs, which is basically the theoretical father of thermodynamics, understood the paradox that we know it today as Gibbs paradox. And in the Gibbs paradox, he concluded that if you want to calculate entropy in a statistical mechanic, you have to think that particles are not distinguishable. And that was the first time we noticed that, even if you look at a macroscopic gas, you should not think that they are identical. They are distinguishable, but in fact they are identical. Because if they are not identical and if they are different, you don't get. So if you mix, for example, two group of gases that are completely identical, but if you think each of these atoms are different, then if you mix them, there is basically you're not doing anything, but the entropy goes up. But in the case that you say they are not distinguishable, so they're indistinguishable, then there is no change in the entropy when you mix them. So Willard Gibbs for the first time said that you cannot really think even like macroscopic gas molecules are identical if you really want to calculate the energy in a correct way. So you should have this kind of normalization, and this normalization counts for indistinguishability of the particles, so we are not overcounting. So when you, for example, you have two electrons and you think that these two electrons are different, you say they're two particles. But when you have the same particle but two times repeated, there is a factor 1/2. So this is like a kind of avoiding the overcounting and making entropy extensive. But the whole point is that eventually we migrated from the picture that the macroscopic world is not identical, but the atomic world, electrons are identical. So when we started to have classical mechanics was suggesting that particles can be distinguishable. When the statistical mechanic came on, it says no, there is some paradox in the definition of entropy. So even the macroscopic gas molecules should be indistinguishable. And then we have quantum mechanics, which says 100% agree with the statistical mechanics. Things are not really distinguishable. There is no way that you can say this electron is here, is electron A, the other one is electron B. So eventually we came with the notation of field. So field means indistinguishable particles. So I mean, there is some this particleness, or I can say electrons versus electronness. Imagine instead of having this image that there are electrons everywhere, and this electron is electron 1, this electron is electron 2, the other one is electron 3, A, B, C, you name them, you should say there is electronness everywhere. So this electron field is everywhere. So that's why all the electrons are identical, because they are all part of the same field. So they are not like really distinguished particles. I mean, then where did they come from? So what if there is one field and all of these particles are a part of this one field? Then some part they have more electron. You say there is more electron there. There is more electronness there. There is less electronness there, means there is less electron there. So if I play this video here, you notice that this is the picture. This is like a very simple picture of quantum field theory. In quantum field theory, it says you don't have electrons going around. Electrons are basically everywhere in every side of the space-time, and then all you have is this oscillation of the electron. So the idea of field really made this indistinguishability very important for us. Like the two electrons are the same everywhere, because there is one field everywhere. Next question is why does particle physics need a special relativity? Because some people think that particle physics only requires quantum mechanics. That's true, but quantum mechanics plus special relativity, because special relativity, the first reason we need a special relativity is that the rest mass is not conserved in special relativity. So in classical mechanics, the rest mass was conserved, and the energy was conserved, and momentum was conserved. But in a special relativity, you unify them into energy momentum conservation, and then the rest mass is not conserved. So rest mass can turn into kinetic energy. And this is the famous Einstein equation, equal to mc2. For example, when you have a decay, this is one of the examples. You have a decay, for example, a neutron decays into a proton and electron and the antineutrino of the electron. And then if you sum the mass of these particles and compare to the sum of mass of the neutrino, you notice that the sum of these masses are less than the mass of this neutrino. And some mass is missed. And it just turned into energy, and that's because the rest mass is not conserved. So you need a special relativity for that. And the notation of particle antiparticle is also coming from special relativity, because in special relativity you have two modes of energy. In classical mechanics you don't have. So if you expand this energy in terms of basically a Taylor expansion of this power law, you get the rest mass plus the first order kinetic energy. So this is a classical kinetic energy, and this m is the rest mass. So rest mass is a part of energy, but it can turn into momentum. So this is why you need a special relativity, basically for these two topics. You need this logic of the rest mass is not conserved, and you also have this particle antiparticle notation, which gives you two kind of orthogonal direction of time evolution, this particle antiparticle. But I have this quantum field theory videos. These are really boring videos, but if you go to I think one of them, number 3 or number 4, I explain how this particle antiparticle in the Dirac videos. You can see how this Dirac concluded that there must be particle antiparticle before we even see any antiparticle. So the first, Dirac came up with the conclusion that electron should have a partner, and this partner should have a positive charge. But he made a mistake, and he said at the beginning that this partner should be proton. But the problem was that a partner of the particle need to have the same mass as those particles. So proton cannot be the case, so call it positron. And positron were discovered later. And positron was the first antiparticle we observed, and it's very similar to electron, very, very similar to electron. But we concluded that from the logic of special relativity, just incorporating into quantum mechanics. In general, you have, you always have to deal with the matter of a scale in physics. You have different scales. You have different scales. Let's say I compare size and speed, and size is not really well defined. Size can be linked to energy, but here by size I mostly means just physical size. So the idea is that the small size you need quantum logic. Quantum logic is mostly about how to connect an input to a probabilistic output. So there is not like a kind of well-defined trajectory from initial state to final state, and that's about quantum logic. So you have non-relativistic quantum mechanics in the lowest speed. So hydrogen atom, for example, can be explained in the framework of non-relativistic quantum mechanics. In classical mechanics, you can basically explain planetary motion, biological world, even biological world can be explained. Even it's it's in a micron, the order of magnitude of the size, but even classical mechanics is sufficient still to explain biological world to a degree, not completely. You need definitely some quantum correction that comes from chemistry. But then you have this high speed. So when you go to high speed, you really need to count time dilation. It's really important in the context of particles because they decay, and particles decay. And this is one of the very, very important part of the particle physics, is that if you have a particle that decays very fast, if you accelerate it to the very high speed, you will see that it decays later, because the internal clock of the particle with respect to the lab is going slower, so you observe the decay later. If you really need magic, these measurements are done, and if you accelerate particles into high speed, you see that they decay later by our perspective. And this is very interesting. We need a special relativity because cosmic rays are fast. They are really near the speed of light. High energy particles are fast. So you need to integrate quantum mechanics and special relativity into a context, and that's quantum field theory. Quantum field theory is a very kind of interesting subject, and it's quantum procedure of the field, and field is kind of responsible to keep the properties of relativity, causality, and locality that you need. So with this introduction, now we hope that we can start learning about the history of particle physics and what did we learn eventually in the 20th century up to this point, and what is the current status of the particle physics. So thank you so much for watching this video, and I see you on the next video.